Chapter 4.6, exponential growth and exponential decay function. Okay, we have a function. Let's use n of t instead of f of x. So let's say here is an equation. N of t equals n0 times e to the kt. Okay, in this case, n0 is the initial amount. So like a population, there's an initial population like in 2010, and after 10 years, after 10 years pass, then there will be a new population. So n0 is the initial amount, and the exponent kt represent that t is the number of years or seconds or minutes. So t represent the time, and k is the rate of growth or decay. If k is positive, then it will be the exponential growth, and if k is negative, then the graph will be exponential decay. So n of t is the amount remained, or the number of people. So it represents the number after the time t. So from this equation we can graph this. So the graph will be an exponential growth if the value of k is greater than 0, and if the value of k is negative, less than 0, negative, then it will be an exponential decay. So the graph looks like this. The t starts from 0, so we don't have a negative value, and this is n of t. So starting from the initial amount n0, it will exponentially increase. Exponential decay. So exponential growth. So from this function, n of t is equal to n0. Starting from n0, exponential form with the exponent kt. Okay, for the exponential decay, if the k value is negative, then starting from n0, this is exponential decay, so it decreases exponentially like this after time t. So based on this, either exponential form is growth or decay. Let's try an example about population. Okay, example 1. Okay, there's a city, and the population in that city in 1995 was 16,400. And after 10 years, in 2005, the population increased to 20,200 people. So 16,400, this will be the initial amounts of the population. In 1995, 16,400 will be the initial population, so we can use it as n0. And after 10 years, so 10 years has passed, so t will be 10, and the population after 10 years, the population is 22,000. So that is our n of 10 value. So when we write this one in a exponential growth function, let's use this one, the function n of t is equal to n0 times e to the kt. So based on this, let's plug in all these values so we can find k. So n of t, since t is 10, this will be n of 10, starts with n0, and e to the k, and 10 is k out, so the t value is 10. So we still know the values of n0, the initial amount, and the amount after 10 years. So n of 10 will be 20,200, and 0 is 16,400 times e to the k times 10. So from this equation, we have all the values except k. So from this, we will find the k, and then k is in the exponents, so we have to get rid of the base e. So in order to find the k, let's divide each side by 16,400. So we have only one exponential form on the right hand side. So divide each side by 16,400. The right side is 10K. And from this, we can eliminate this E by taking natural logarithm on both sides. So okay, let me write this one again so that you don't get confused. 10K. So now let's take natural logarithm on both sides. Natural logarithm on both sides. Okay, then the right hand side, you can just eliminate, you can just move this exponent 10K to the front, and this ln E will become 1. The left side is unchanged. Okay, since this ln E is equal to 1, you can just remove it. So from this, we found K. You can divide each side by 10. So it will be 10 natural logarithm divided by 10. So this is the value of K. So once we use the calculator, then this one, the value of this will be approximately equal to 0.0208. Okay, so let's plug this back in the original model. So n of t is equal to n0. So n0 is 16,400 times e to the k is 0.0208 t. So we have this function. So okay, we have this function. Okay, so based on this function, once we provide the t value, then we can estimate or predict the number of populations. Okay, so letter B is predict the population of the city in 2010. So in 2010, what would be the population? So in this case, we have to find t. So t is 2010 minus 1995, because 1995, the initial amount is based on the year 1995. So subtract this, then we have 15. So t will be the 15 years. So plug in 15. So from our function, replace t with 15. And then use a calculator to find the result of this, and then evaluate these numbers. So it will be approximately 22,400 people. This is nearest 100th. So it will be about this many people. We can predict this many people in 2010. So it's important that we have to understand the formula, the function, the growth function or decay function. So starting from this function, find out the k value, because we have all the values for the other variables. So find the k using logarithm, in this case natural logarithm, because the base is e. And then find the k and then replace it back to the original function. So from this original function, and then replace t value so that we can find the final amount. In exercise example 2, okay, we will find the amount of phosphorus 32 that remains in a sample after t days. Okay, this is related to the half-life questions. Okay, half-life means the initial amount becomes half, reduced by half based on the material. So in this phosphorus case, after 14 days, then the amount will be reduced by half. So we can use the exponential decay function. So let me write the decay function, n of t. Okay, let's change the color. The n of t is equal to the initial amount n0 times e to the kt. And we know that 14 days is the value of t. So after 14 days, the initial amount will be reduced by half. So the initial amount is n0. So n0 will be reduced by half. So it will be 1 over 2. 1 over 2 or 0.5. n0. After t days. So the value of t is 14 days. So write 14. And then we can cancel out this n0. We can cancel out this n0. So 0.5, which is 1 over 2, is equal to e to the 14k. So from this, we can find the value of k. Okay, by the way, the half-life of phosphorus is 14 days. Okay, let's check this right-hand side. The half-life of carbon-14 is 5,730 years. This means, for example, 1 gram of carbon-14 will be reduced by half after approximately 5,730 days, 30 years. And there are other half-life informations like radium and poloniums. So we can apply these values when we calculate amount left after certain years or days. So this is one of the examples using phosphorus. So we just found that 0.5 will be equal to e to the 14k. So from this, let's find the value of k. Okay, so we can take natural logarithm because the base of the exponential form is e. So take natural logarithm on both sides. Then we can take this exponent out. So the left hand side is natural logarithm of 0.5. The right hand side is 14k times ln e. And ln e is equal to what? 1, right? 1. So this is equal to natural logarithm 0.5 is equal to 14k. So finally, k is equal to, divide each side by 14. So that's the k value. So from this k value, using a calculator, the exponential growth rate, this is decay rate, k will be, use a calculator, then it is something like approximately negative 0.0495. As you see, the sign is negative because natural logarithm of 0.5 is negative. Natural logarithm of x, where x is less than 1, between 0 and 1, then that's negative. Do you remember the graph? The natural logarithm graph of this graph is this. And this x-intercept is 1. So if the x value is between 0 and 1, then the natural logarithm is negative. So we have a negative value. Since k is negative, this is exponential decay. So finally, we can write the function, exponential decay function, as n of t is equal to the initial amount, let's say is n0, and then e to times e to the k is negative 0.0495 t. So this will be the exponential decay function. Okay, in example 3, okay, we will estimate the age of a bone if the remained amount of carbon-14 is 85%. So if 85% of a carbon-14 is remained, then we want to find the age of this. So in this case, we can use the half-life formula, but we can use a different one. Since this is about half-life, so after 5,730 years, the half-life of carbon-14 is 5,730 years. So after this many years, the amount will be reduced. What we know is 85% of the initial amount of the carbon-14 remained. So we can replace this N of T with 85% of the initial amount and 0. So we can write it as, change the color. So N of T will be 0.85 and 0. So 85% of the initial amount is remained. So N0 times. Okay, now the base is 0.5. The base is 0.5 because this is half-life. So every 5,730 years, the amount will be reduced by half. And multiply by T over H. H is the half-life of carbon-14. So that is 5,730. So the reason that we divide T by 5,730, the half-life, is if T is 5,730, then the exponent will become 1. So actually, we are reducing N0 by half. Something like this, N0 times 0.5. Because after 5,730 years, then this will become 1. So the initial amount will be reduced by half. So this makes sense. So we can divide T by 5,000, the half-life years. So from this, we can cancel out N0. So the left-hand side is 0.85. The right-hand side is 0.5 raised to T over the half-life. Because since we want to find T, we have to use logarithm. So in this case, let's use logarithm or natural logarithm. Anything's fine. So let me write this one again. And then take the natural logarithm. So take natural logarithm on both sides. Natural logarithm on both sides. Then the exponent on the right hand side, from the right hand side, the exponent moves to the front. Then multiply by natural logarithm of 0.5. Okay, from this, we can multiply both sides multiply the equation by the denominator 5,730, so that we can cancel out the denominator, and also divide each side by ln 0.5, so that we can remove this ln 0.5 from the right hand side. So the t value, use the calculator, then the t value will be, this will give us the t value approximately equal to 1,340. So this will be the year. So the bone is 1,340 years old. So in this case, we used a different function, a little bit different, because this is half-life. So the function looks like this. The initial amount times 0.5 raised to a power that is t over the half-life. Okay, here is another formula that is called the compound interest formula. So in this formula, we can have three types. The first one is the amount compounded yearly after 10 years. Then the formula will be the amount after t years will be p times exponential form, 1 plus r and exponent t. And the second type is we can have an amount compounded n times per year, like quarterly, compounded quarterly, or compounded monthly, or daily. Then we will divide this annual rate R by the number of times. So R over N will be the rate. And then there are N times per year, so we will multiply T by the number of times per year, NT. And the third one is we can compound continuously. This means the N times per year will be infinitely many. So if N goes infinite, then we have the number 3 formula compounded continuously, which is A equals P times ERT, PERT. Okay, let me prove number 1, the compounded yearly. So after 1 year, let's say P is the principal. So after 1 year, you will get the total amount will be your principal plus the interest amount. The interest amount is multiply your principal times the rate of the yearly rate, which is R. So P plus PR is equal to factor out P, then the principal is multiplied by 1 plus R. We will multiply the principal means the previous amount. So after 1 year, after 2 years, after 3 years, the total amount will be the previous amount, P, and then this amount will be multiplied by 1 plus R. So after 2 years, then it will be the amount in the first year, after the first year, times 1 plus R. So 1 plus R will be multiplied every year. So A1, the amount after the first year is P times 1 plus R, multiplied by another 1 plus R. Then this will be P times 1 plus R squared. If you keep doing this, so after 3 years, then the total amount A3 will be A2 times 1 plus R. And A2 is 1 plus R squared times another 1 plus R. So P times 1 plus R to the third power. So as you can see, there is a pattern. So after 3 years, the exponent becomes 3. So if you keep going this, and after n years, then the total amount will be, so which is AN. We can use A. That will be the principal times 1 plus R raised to the nth power. So that is after n years. So why don't we use t years? If we use after t years, then this will be t. So after t years, the total amount will be this one. So this is the formula for the amount compounded yearly. And then if this is compounded monthly, like for example monthly, then number 2, we can prove number 2. So if there are compounded monthly, then we have to divide the yearly rate by 12, because there are 12 months, and there will be number of times there will be 12 times per year, so multiply this by t. So the total amount will be principal times 1 plus R should be divided by the number of months, 12. So since there are 12 times per year, multiply t by 12. So this is the amount compounded monthly. If this is quarterly, then n should be 4. So quarterly, then this amount should be 4. If this daily, then we can replace this by 165. Okay, so if there are n times, compounded n times, then the amount will be P times 1 plus R over n raised to the nth power. Okay, and for number 3, Okay, for number 3, this is a little bit complicated. So if n goes infinity, okay, for this one, let me write the formula first. Okay, for the formula for continuously compounded, okay, we have this formula. So let's find out how we got. This is second formula, which is compounded n times per year. So from this formula, we will derive to make it a formula for continuously compounded. So it will be 1 plus, compound continuously is PERT. So we will find out how we got this one from this formula. So for this, we gotta know this. Okay, look at this red equation. Okay, here is 1 plus 1 over c. 1 plus 1 over c. This is raised to the c power. And then if c approaches infinity, then the result will be getting close to this number, 2.718281 and so on. So we call this E. So E is not a variable. Actually, E is a number, 2.71. So whenever this C value approaches infinity, gets really large, then this total value will be close to the value E. So let's find out how we got this. Okay, first of all, okay, let's make R of n. Okay, let's C is equal to R over n. C equals R over n. Then reciprocate each side. So we have 1 over C is equal to R of n. Reciprocate. And or we can have, if you divide this by R, then we have n equals CR. N equals CR. Okay, then from this, let's replace the equation. Okay, here, A is equal to P times 1 plus R over n raised to the nt. Okay, R over n. We just found that R over n can be written as 1 over C. So why don't we replace this R over n with 1 over C? And then n is equal to CR. So CRT. Then we can rewrite it. So let me use a bracket. 1 plus 1 over C. And the exponent C remains the same and raised to another power RT. And then based on this information, we can replace this bracket with E because C approaches infinity. Why is it infinity? Because this is compounded continuously. Continuously means the number n will be infinite. So this number will be replaced by the number E. So PE, the exponent is RT. So we have this function. A equals PERT. So for compound interest or compounded, for the compound interest, there are 3 types of formulas. One is compounded yearly, compounded n times per year, like quarterly, monthly, or daily, or in seconds, or compounded continuously. So based on the information, we can use one of these 3 formulas. So let's try example 5. Example 5, we will find the balance after T years. On $800 invested at an annual rate of 6% compounded continuously. This one says continuously, compounded continuously. And we want to find the balance. That means we will find the amount after 4 years. So 4 will be 4 years. So T value will be 4. And $800 is the initial amount, the principal. So the principal, so $800 will be the value of P. So using the formula for compounded continuously, the amount is PERT. We gotta use this one. So the amount will be replace P with $800. E times the rate is 6%. So 6% means the decimal is 0.06. Okay, so the exponent is 0.06 times t. T is 4 years. So using a calculator, this will be 800 times. This exponential form will be approximately 1.271 to something. So this is approximately equal to $1,017. So this will be the amount after 4 years. Example 6, we want to find the time required for money invested at an annual rate of 6%. And that will be doubled in value if the investment is compounded semi-annually and continuously. So if it's compounded semi-annually, that means there are twice per year. So this means n will be 2. And the rate is 6%, so 0.06. So let me write a formula for this one. So you compound semi-annually, so we will use the second formula. So the total amount will be the principal times 1 plus r divided by the number of times per year, and the exponent is nt. So we want to find out the time so that the principal will be doubled. So this amount A will be doubled, so it will be 2p. Because P is the principal, the initial amount, and P is doubled, so it will be 2p after t years. So it will be 1 plus R is 0.06. The number of times per year is twice because this is semi-annually. And then raised to the 2t. So we can cancel out this p. We want to find the value of t. So okay, let me write it this one again. And then we can take natural logarithm so that we can take the exponent 2t out. So take a natural logarithm on both sides. Okay, write this one again so that we can use red pen. So from this equation, take natural logarithm on each side. So the left hand side is natural logarithm of 2, and 2t, the exponent 2t moves to the front. And the ln stays. Okay, in order to find t, we can divide each side by 2 and the natural logarithm. So ln t over divide by 2, those coefficients on the right hand side, 2 and natural logarithm of 1 plus 0.06 over 2. So this will be the t value. So using a calculator, t will be now approximately equal to 11.72. So after 11 and around between 11 and 12 years, the amount, the principal, will be doubled in this case. Okay, let's try another one. Next one. Now the interest is compounded continuously. So since it's continuously, we will use the third formula, which is A equals PRT, PERT. PERT. And then same as this one, so the amount will be doubled, so it will be 2P is equal to P times E, and the exponent is 0.06 T. And then we can cancel out P, so 2 is equal to E to the 0.06 T. Take ln each side. Then we can take the exponent out. So this ln 2, 0.06 T natural logarithm E, and then this natural logarithm E becomes 1. So ln 2 is equal to 0.06 T. So finally you can divide each side by 0.06. So that's the value of T. So T is approximately equal to 11.55 years. So if we compare these two, it's pretty much similar. 11.72 and this is 11.55 years. So probably this is more accurate. Okay, we have another formula that is related to a restricted growth model. So one of them is logistic model. Okay, logistic model is this. The maximum population is given. So as time passes, the population approaches certain number. Let's say this is C. So it looks like this. The population at time t will be C over 1 plus A times e to the negative bt. So from this, this one looks a little bit more complicated. Okay, C will be the maximum population. This is called carrying capacity, and B is the growth rate, and A is a percentage growth. So A is C minus the initial population divided by the initial population. P0 is the initial population. So once t gets infinity, let's say this one. Okay, A is a number and negative B is a constant. T is number of years. So basically the exponent is B, exponent is negative. So the result of this will be the graph. This graph is decay. This is a decay function. So as time increases, this value will decrease and getting close to 0. So this y value is getting close to 0, approaching 0. So this will be 0. So A times 0 is 0. So the denominator is 1. So basically this will be C over 1 if time gets large and large. So the population will be approaching C, the value C. So this is a population, this is a logistic model. So we can try this and let's see what happens. So let's look at the next question. Example 7. Okay, this is about using logistic model. So in the year 2005, there were 200. The population, the coyote population was 200, and after 2 years, in 2007, the coyote population became like 250. So in this case, the carrying capacity of this area is given to 500 coyotes. So from this, okay, letter A is find the growth rate constant for this logistic model. So with that, the growth rate constant is B. So from the logistic model, we have to find B. So for this, okay, C is given. The C is the carrying capacity, which is the maximum population will be 500. And T will be 2 because after 2 years we know the coyote population. So we got to find the value of A. Okay, A is, as you see from the above, A is the difference between carrying capacity and the initial population divided by P0. So A is carrying capacity minus P0 divided by the initial capacity P0. And C is 500, this is the maximum. P0, the initial capacity is, the initial population was 200 divided by 200. Then this is equal to 300 over 200. So that is 1.5. So the A value is 1.5. So let's plug in this to the largest model and then find B. Okay, so let me just explain this one again. The 200 is the population, 200 is the P0, the initial population, and C is 500. Okay, so from here, so the largest model is P of T is 250 after 2 years. C is the carrying capacity is 500 divided by 1 plus A is 1.5 e to the minus negative B times 2. So that's the equation. So from this equation, let's find B. Okay, first of all, we can use cross multiply. Cross multiply, so 250 times 1 plus 1.5 e to the negative 2b is equal to 500. And then we can divide each side by 250 so that we can separate this exponential form. So divide by 500, 500 by 250, so there will be a 2. Then 1 plus 1.5 e to the negative 2b is equal to 2. And then subtract 1 from each side. So it will be 1. And then divide each side by 1.5. So 1 over 1.5. Okay, we are getting close. So we want to find B so that the B is in the exponent. So we gotta remove the base E. So why don't we take natural logarithm on both sides? So there is the natural logarithm e to the negative 2b is equal to natural logarithm of 1 over 1.5. Then the exponent moves to the front. Okay, that's natural logarithm. ln e is equal to ln 1 over 1.5. ln e is equal to 1, so negative 2b is equal to natural logarithm of 1 over 1.5. Now divide each side by negative 2, or multiply the reciprocal of negative 2. So multiply negative 1 over 2. So multiply each side by a negative 1 over 2. Then we have this. So using a calculator, the B value will be approximately equal to 0.2027. Okay, more than 3255. So this is the growth rate constant. So from this, we can rewrite the equation. P of t, the largest model, P of t is equal to C value is 500 divided by 1 plus A value was 1.5, right? And e to the negative. The B value is the one we just found, 0.20273. Okay, 255 T. So that's the largest model for this. So from this, if any value of t given, then you can find the population, or you can, if a population is given, then you can find the number of years. Okay, the next one is we want to find how many years will be required for the cohort population, which is 400. So in this case, 400. So we want to find time t, and 400 is the output. So p of t will be 400. So let me use the model that we just found in letter A, so that we can find t. Okay, the exponent is 0.20273. Let me write up to here. So let's simplify this so that we can find t. So cross multiply, we do the same thing, cross multiply, so it will be 1 plus 1.5 e to the negative 0.20273t is equal to 500. Divide each side by 400, so 1 plus 1.5 e to the negative 0.20273t equals 500 over 400. So that is 1.25, right? And then divide each side, and then subtract 1 from each side. 273t is equal to, this is 1.25. 1.25 minus 1. Then divide, then this is equal to, okay, we are doing a lot of writings here. And 0.25. And divide each side by 0.5, negative 0.20273t is equal to 0.25 divided by 1.5. And then finally we take natural logarithm on both sides. So take natural logarithm on both sides. The right side is this. So the exponent moves to the front, negative 0.20273t. Natural logarithm e will become 1. The right side is same, unchanged. And then divide each side by the coefficient. So it will be 1 over negative 1 over 0.20273 multiplied by natural logarithm 0.25 over 1.5. Then using a calculator, t will be approximately equal to 8.8 years. So after 8.8 years, so that will be, the initial year is 2005, right? 2005. So 2005 plus 8.8 is 2013. So approximately in the year 2013, which is 2005 plus 8.8, 2013.8 years, the coyote population will be 400. In this exercise, example 8, let's find the time t when the velocity is given, 70. So just plug in 70 for the velocity, and let's find t value from this equation. Because first of all, we have to divide each side by 82. So 70 over 82 is equal to 1 minus e to the negative 0.390. And then, okay, move 1 to the left, or, okay, move 1 to the left. So, subtract 1 from each side. Okay, then this is equal to, okay, 1 is 82 over 82, so it will be negative 8 over 82. Okay, negative. Okay, let me. Okay, this is 7 minus, so 8 over 82. Sorry. Over 82 is equal to this. So we can minus sign here. So we can eliminate, multiply each side by negative. And then we can reduce this 12 over 82 by, so divide by 2, then this will be 6 over 41. And multiply each side by negative, so we have the exponent, this. And then finally, we can eliminate the base e by taking natural logarithm. So natural logarithm of 6 over 41 is equal to, okay, take the natural logarithm. Then natural logarithm of 6 over 41 is equal to, take the exponent out, negative 0.39t, and ln e becomes 1. Okay, always make sure that ln e is equal to 1. So divide each side by negative 0.39. So natural logarithm 6 over 41 divided by negative 0.39. So that's the value of t. So t will be approximately equal to, use a calculator, then there will be 4.9277246. Okay. So after like around 5 seconds, the velocity will become 70. Okay, for this one, okay, there is a horizontal asymptote, that will be 82. Then explain the meaning of this asymptote. Okay, so the velocity equation is this, and then if we distribute, then the velocity will be 81 minus 81 times e to the something. So why don't we graph this using transformation? So it's much more easier to understand. So the graph of e to the negative power will be this. Let me use this one. E to the negative power is this. So this is e to the negative 0.39t. And then if you plug in, multiply this by negative 81, let's say this is 81 times e to the negative power. And if we put the negative sign, then this will be reflected across the, in this case, t-axis. Reflect across the t-axis, something like this. So this will be negative 81 times e to the negative 0.39t. And then we have 81. So we will add 81 to this one. So that means shift this graph 81 units up. Let's say this is 81 units up. So the horizontal distance, the x-axis, the t-axis will be this one. So this one is moved 81 units up. So something like, it will be something like this. Okay, so 0, if this is 0, then 0 is minus 81. So something like this. So as you can see here, this is the horizontal asymptote. As time increases, as time approaches infinity, the velocity is approaching what? The value 81. So 81 will be the maximum value where the graph approaches when s-axis increases. Okay, or you can find this. You don't have to graph it. If you see this, if t approaches infinity, then this wheel approaches where? 0. We're getting close to 0. So 1 minus 0 is 0. So we have 81 times 1 minus 0. So the velocity will be getting close to 81 as time increases. So the horizontal asymptote means it's the velocity which is the maximum velocity where time passes. So this maximum, so the speed will approach 82 but never exceed, but actually never become 81. So is it 81 or 82? Sorry, it is 82. Okay, I made a mistake. So this one is 82, not 81. So they have to be, so the velocity is approaching 82 but never exceed or never become negative 82. Okay.